So before we begin, I'd like to take a moment to acknowledge that this webinar is being hosted today from Amasquatsi Wiskagan, or Beaver Hills House, in Edmonton, Alberta, on Treaty 6 territory, the traditional lands of the Cree, Dene, Blackfoot, Saulteaux, and Nakota Sioux peoples, and a homeland to the Métis Nation of Alberta. As someone whose family includes the late Dr. Joseph Couture, an elder and thinker who spoke of learning through relationship and metaphor, I recognize that this acknowledgement is not just about geography, but about responsibility. It's an invitation to ground our work in respect, curiosity, and reciprocity, values Dr. Couture championed throughout his life. May we carry that spirit into today's conversation. Now I'll hand it off to my colleague, Jonathan Heseltine. Jonathan.
Thanks, John. There we go. Hopefully you can see my screen. Welcome to our next installment in the webinar series on new technology for well remediation and decommissioning. I'm Jonathan Heseltine, and I'm going to be moderating this session. So we'll get to the speakers in short order here, but first a quick introduction. So if you're not familiar with Innotech Alberta, we are a subsidiary of Alberta Innovates, which is a provincial crown corporation that drives innovation and R&D and commercialization in Alberta. So Innotech is a service provider under that organization, and we help bridge the gap between early stage research and commercial end use, so very much applied research. Innotech works in a wide range of industries, including materials and manufacturing, plant sciences, environment, various industrial processes, and resource recovery. But our energy group has been working in the area of well integrity and well abandonment for several years, and holding these webinars as new technologies arise that we'd like to discuss with the industry. So a bit of background on the problem we're trying to solve. Wellbore leakage affects all types of wells and ages in the oil and gas industry worldwide. So it's a widespread problem. As you can see in the image there are numerous potential leak paths in a wellbore where gas or other fluids can flow into aquifers or to surface. And needs to be resolved. So alternative barrier materials and the enabling technologies that go along with them are novel materials that are suitable for sealing these wells. So there's quite a range of materials that are being developed and commercialized, including molten metals, thermal setting resins, geopolymers, chemical precipitates, biomineralized materials, in situ shale and other natural materials, mechanical methods, and others. So a really wide spectrum. With these types of wells, it's often the leaks that are difficult to repair, and due to regulations, when the well is being finally decommissioned, all of those leaks must be completely sealed off. So we're looking for alternative barrier materials or technologies that have characteristics that let us do that. So I won't read this list outright, but we're looking for the types of materials that can squeeze into small flow paths, cure into an impermeable material, and that can be placed properly in the presence of other fluids and the chemical and temperature environment. After they're placed, they must seal for eternity. So they must be resistant to corrosion and the other downhole conditions. We know that all wells might be similar, but they're all different in their own ways. So we're not looking for a silver bullet of one material that will solve the problems. We need a range of technologies to choose for a particular application. With that, Innotech has been involved in a joint industry project that's now wrapping up with a mission to expedite the development and understanding of these types of new barrier materials. The methodology follows a pretty logical process. We selected 5 products based on the participants' interests and expectations. Technical review of those materials allowed us to plan our lab testing program. So in Innotech's lab testing, we've developed a that's quite pragmatic. We are trying to simulate the downhole environment for the placement and sealing and long-term durability of these materials. When the materials have gone through the lab testing protocol, we have now completed 14 field trials with these materials. And then, of course, as a collaborative, data sharing is a very important part of the process. So the objectives of this work, define the suitable applications, sort of the operational envelope and best practices for these materials. To understand what well we use or can use them in, we need to understand how they work and where they're best applied. With that, we start to understand and realize that there are regulatory and technology gaps that we can address. Working with the material developers, we can optimize products. Again, we're sharing the data and discussion within the consortium and publicly. And ultimately, with the understanding and development of these materials, they may become routine solutions to a widespread problem. In terms of the broader industry benefits, of course, we're looking for a functional improvement compared to cement or other methods where we can have internal sealing of wellbores with confidence and understanding. This will lead to an emissions reduction. There's a direct leakage of the gas from the wellbores, but also emissions due to the operation of the intervention. The associated with decommissioning the worldwide inventory of wells is very high. So some industry groups have targeted a 35% reduction in decommissioning costs. And there are other benefits such as reclaiming land use where the wells are and reducing other risks such as the liabilities of the suspended well inventory that are needing to be decommissioned, risks of groundwater contamination, and then health and safety associated with these wells. So you can see in the image there, we have a lot of participants in this project, funders and technical providers, as well as operating companies who are providing their guidance and wells for the field portion of the study. So to get into the technical results of this work, as I said, it's wrapping up, but just a few observations. What we've seen is that these materials do indeed have an envelope where they're best suited. So the lab testing work to understand which types of wells these are best applied in. The lab testing, due to its nature, tends to look at the material's performance, technical performance. When you move into our field trials, we now have the whole as a system, and the geometry of that system and the requirements, as well as the chronological deployment process, are all considerations in planning the intervention. So with that, full evaluation of these materials, you must look at the technical performance, the sealing, the longevity, displacement of fluids, contamination, all of those things, but also in the field, have to consider safety and environmental considerations, as well as time and cost of deployment. And then finally, collaboration yields major results. Major benefits. We've seen that throughout this project. The spirit of the is very much collaborative with the operators and with the technology vendors. Everybody wants these solutions to work. So there's been a great effort to share the results, and I think everybody benefits from that. So in terms of next immediate steps, the public report from the project work will be released very, very shortly. You'll likely find a link on Innotech's website or NZTC or PTAC, depending on your preference. There are currently additional field trials going on for through tubing abandonment procedures. So the idea here would be to plug a well without pulling the tubing first. And we have additional products being tested in the lab right now. So those are the immediate next steps, and we have other work planned. So with that introduction, we're going to move into the presentation component of the webinar. We have 3 speakers today who I'll introduce briefly here. Our first speaker is Oleg Ishkov. He's the CEO and founder of Rockit. Next, we'll have Lennox Leotaud. He's technical marketing supervisor for Well Armour and also the president and co-owner of Olive and Branch Merchandising and Distribution. And then our final speaker will be Craig Brown, the founder and inventor of UVT Solutions. The structure of the webinar, as John mentioned earlier, we will have a speaker followed by about 10 minutes of Q&A. So please type your questions into the chat while our speakers are presenting, and I will read them out following the presentation. If we have some time at the end, we can circle back to any unaddressed questions or any questions for any of the speakers. And so with that, I will turn it over to Oleg from Rockit.
Thank you, Jonathan. So I'll share the screen. Please let me know if slides are appearing.
Yeah, I can see them now, Oleg.
Right. So my name is Oleg, and I'm representing Rockit. We are based in Edinburgh, in Scotland, and we are early stage oil and gas well sealing technology. But our goal today is to introduce the technology, what specifically we do, and one of my target is also to establish a road path for the future collaboration for the potential field pilots. So what essentially we are offering, so Rockit is the novel method to seal oil and gas wells using the barium sulfate mineral. And by doing so, we offer permeable and much more economical solution that we believe is currently used in the industry. And as Jonathan mentioned, so the problem we are solving is the huge and the global one. So the number of wells with well integrity issues is significant. We are talking about tens or hundreds of thousands of wells. And so the wellbore leakage affects plenty on different variety of the wells, and we are talking about different rates as well of the leakages. But overall, the key requirement is that when it times to abandon the well, it must be zero leakage. And as Jonathan mentioned, one of the hardest challenge is actually to seal the smallest pathways, because the currently industry, the current approach is most solutions are install the plugs and they cut the flow from the wellbore to the surface, right? But unfortunately, the leaks still persist. And if you're talking of cement, obviously we are not targeting to completely replace the cement. Cement is good, it's fantastic material. But obviously in the industry, there is well-documented issues with cement, and it cracks, it brittle, so there is a limit on the due to viscosity in the solids present in cement and the temperature stability. So at the moment, there is a demand for the new solutions. So Rockit is different in this case. So we are offering a seal, and So we're creating a barrier at the source. We are cutting the flow from reservoir into the wellbore. So in this way, the plugs, cement, or some other metal alloys materials can be better protected from the future degradation. So in essence, our technology, we transform rocks into barriers themselves. And we use acid-resistant long-lasting minerals, which is very well known in industry. It's barium sulfate, and this material is naturally resistant on the geological timescales. On the left, you can see this CT scan of the rock core sample that we sealed with barium with our Rockit seal, and basically this is the illustration, so we can penetrate into the smallest pores and seal within the rock, right? So, and also the technology we offer is using the solids-free aqueous solutions, 2 of them. We don't use any other scale inhibitors, or we don't require any nutrients. So it's just 2 solids-free liquid aqueous solutions pumped into the well, and then on a reaction in the formation, those chemicals react and precipitate in significant amounts minerals. So we call it rock within the rock. By doing so, using the solids-free and low viscosity solutions, and viscosity of our solutions is very close to the water, so 1.4 centipoise, we reduce the risk of fracturing. So basically, we can inject whenever the water can be injected. So we can address the smallest flow path, and because of this, we can also use this opens up a door to use our solutions as the potential for rigorous application, because in a sense, it's just aqueous, it's just basically salty brine or aqueous solutions you need to pump. But the material properties, barium sulfate, opens us a door for the permanence. Basically, the barium sulfate is one of the hardest scale known in the industry. It's very difficult to remove. As soon it adheres very well to steel, rock, and any materials. It withstands most aggressive conditions, high H2S and CO2 content, and it's one of the extremely insoluble mineral known so far. So this is very permanent material. So building on this, we believe that there is opportunity for significant cost and time efficiency, because the standard pumps can be used. There is no tools requirement, so high pressure pump, and the procedures are very well known. Consider this as a squeeze treatment. When you squeeze solutions as very well known, established procedures, established verification process, and the reaction is quick. And then the another advantage that what we kind of come up with in our research and development, that the chemicals we use are already available in the bulk around the globe. So we can scale this with the help of industry partners much quicker, and we believe this could be reduce the barrier for the industry adoption. There is a different applications that the Rockit can be applied. Spanning from the reservoir abandonment to the zonal isolation and cement remediation. And speaking of the deployment options, there is several methods that our technology can be deployed. The very first one is, and again, this is our target and how we think ideally it could be performed, is using the bullheading or using single flow path and iteratively. Because we use 2 solutions, they need to be separated with the aqueous spacer to protect the flow path itself. However, there is also different options of deployment available. For example, we can use the coil tubing, and we spoke with the providers of coil tubing. So if the well is not deep and quite shallow, then the coil tubing can deploy the first solution, then a coil can be pulled up, cleaned, and the second solution can be pumped. So this way, we remove the need of aqueous spacer between the 2 solutions. If well design allows, we can also deploy concurrently through different flow paths. For example, through the production tubing and behind tubing, we can discuss it. Or, for example, the coil tubing that has a concentric coil tubing. And obviously, if specific targeting for the placement is required, our solutions can be deployed via the tool. But this gives the basically a downside that then with the tool you're limited with the volumes. With the bullheading, you're not limited with volumes. You can pump as much as you know. Now, how we plan to take this forward? Well, we don't have pumps or capacity to provide services. So our target is to work with oil and gas companies, but with the partnership with well service companies who has already capabilities, pumps, and their established relationships, who would deploy our solutions to the oil and gas companies, and will take care of the supply chain and basically provide the product. And the product is salts that needs to be dissolved into basically in water and just pumped, right? So where we are at the moment, and how do we see this to take forward? So Rockit is a fully functional prototype. We believe that we are at TRL level 5, and as a note, so our lab has decades of experience actually preventing the mineral scale to precipitate. So we are turning this problem into a solution. We provided a lot of tests, and basically we can hold, we can block the rock and hold 1000 psi pressure differential with no flow on effluent. We can destroy the permeability almost 99% and more. And not just only us tested this technology. Our technology was validated with one of the oil and gas major in their R&D labs. We have a patents granted in the US, in UK, so they both granted. And behind us, we have a very experienced team of oil and gas veterans. So in terms of prototype, we are very confident, and here is the illustration of different extensive lab validation we took. On the left, you can see the bottle tests, basically showing the level of high precipitation. So we achieved not just a precipitation, but in significant quantities, which allows us to block rock or seal the rock quickly. We did transport tests in the sandparks, in the core floods. We did the microfluidics, reservoir simulations, and so on the right you can see the CT scan again. They would of core before and after. And again, in the interest of time, probably we can leave it for the later discussion. But the key message is that we've done extensive lab validation, and effectively the next step for us is to engage with the established partnership to narrow down the commercial case for the adoption, be it cement remediation or the reservoir kind of abandonment and the reservoir abandonment, and then establish the partnership for the field pilots. So if I may, so my ask would be that if there is interest for our technology, we would be very happy to hear from you. And if you supply well candidate parameters, we can then model the deployment, design the treatment, and they provide you cost for the field pilot, and we can take it from there for the future success of the technology. And I hope that in the end, we will be successful in building this sealing technology that will leave no leaking wells for the next generations. So this is our big goal. This is me. Thank you very much. And I would very welcome questions.
Thanks, Oleg. A few questions coming in here, so I'll read them out. The first is from Ken Massich. What sort of reaction time is expected for when the two substances come together in contact?
This is a very good question. I understand the concern with the controllability. The reaction time is, we are talking about maybe minutes to an hour, so not too long. It's not immediate like a seconds. So there is a window for the reactions, but this reaction is quite quick.
And there's just a follow-up to that. Is it temperature dependent, and can that be altered?
It is not a temperature dependent. The barium sulfate mineral precipitation is perfect in this sense. So it's very, the material the barium sulfate precipitates in the range of temperatures from super high to super low. But if it needs to be controlled, and if it needs to be laid, the simplest way to delay is by diluting solutions, because we are delivering very concentrated solutions.
We have one from Tim Shehu. How long does it take for the barium sulfate to form downhole? How good is the bond with the rock encasing? Is there any chance of a microannulus?
Well, so the bond, the 1000 psi pressure differential test probably answers the question on how good is the bond. So we can, under very big stress, it is holding. The next one, could you? I didn't get the question. The second one.
I think the question, is there any chance of a microannulus? And maybe I'll just expand on that. You mentioned maybe an application for cement remediation as well as sealing the reservoir. Have you done any experiments sealing microannular shaped flow pads or cement fissures?
We have not done this specific experiment so. If there is as I mentioned, if we kind of focus on validate on this specific application, and there is a significant driver for this, we can then design next stage of our experimental for those kind of conditions. We were focusing on rock and yeah. So yeah.
Thanks. Question here from Tim Sharp. Can Rockit be drilled out? And maybe with that for me, in your setting procedure, what is left in the well after the operation?
Very good question. So in the well, it is left a solution, the leftovers of the chasing up solution. So there is no need to drill out because the well itself is kind of clean. There is will squeeze and form scale in the wellbore. So as answering this, there is no need to drill out because it does, by design, it doesn't precipitate in the well in the tubing. If this is what they're asking.
Yeah, I think so. From Robin Goad, is the barium introduced in a solution or is it in physical grains? And if so, what grain size do you grind it to?
Mm-hmm. Barium is not introduced as these physical grains. So the key point is solids free. So we have two solutions with aqueous salts. One carry basically components, barium, and another one sulfate. And on a mix, we precipitate barium sulfate. So we start with solids free and end up with the barium sulfate as a mineral in the rock pores, you see?
A question here from Jerry Boyer. Has Rockit done any strength or endurance tests on the product? Are there any pressure or temperature limitations on deployment and long-term applications?
Mm-hmm. Very good question. The strands, if we're talking about the rock strands, this is the precipitation goes within the rock pores, so we believe it will improve the rock strands itself. So it will be function of the rock itself, which is filled and blocked with the barium sulfide within, right? We have not done the material itself because this is the material, the target application is to be inside the small pore space, right? So this is the strands will come from the rock itself mostly, right? What was another one?
Temperature or pressure limitations on the deployment and I guess long-term applications of the permanence of the barrier.
So the pressure and temperature, there is no pressure dependence. So barium sulfate precipitation is insensible to the pressure, and but for the temperature, the only limitation and the kind of basically window of application, we see that its precursors may have range of solubilities at different temperatures, right? So normally, the hotter you go, the solubility increases, right? So it should be no problem. The colder, then you will experience probably start with a little bit less solubilities. So you need to account for this one. But in terms of downhole precipitation, then again, barium sulfate is a perfect material because it's also insensitive to the temperature of when it precipitates. So the only issue I see is potentially if it's going to be extremely cold on the surface, then we'll need to make sure that the precursors don't drop out before they kind of go into warm. But the higher temperature, the better.
Okay.
Yeah.
We've one question here. I think you answered it mainly, but there's a part about chemical interaction with pore fluids. Are there any issues with contamination or interactions with other fluids downhole?
No, it shouldn't be. So this is very typical kind of squeeze type placement when you displace wellbore brines. And again, some of the wellbore brines actually even beneficial for our reactions because they carry, let's say, the significant scaling ions like barium. And for the oil, if you have a water, if you have oil filled pores, we have an option, and our precursors are very well designed, so we can even have a MEG. Basically, it's mutual solvent, so we can displace even oil-filled pores. We can talk a little bit more, but very good question. Thank you for this. We can even address the oil-filled pore space as well, if it's required.
Just looking. I do have a question. So what we've seen with precipitate type sealants is that it takes multiple stages to seal a flow path, both in the lab and in the field. And I think it's due to the volume of precipitate you get as products based on the reactants. There's always kind of a volume fraction there. And you had that bottle test there where it looked like your precipitate volume was quite high compared to the total volume. But have you seen that behavior in the lab where it takes a few stages to seal the core? And if so, how many?
Mm-hmm. This is a fantastic question. We are aware of this issue, right? With, let's say, another approach for the mineral precipitate. So let me spend a little bit 1 minute to address this issue. You're absolutely right. If you don't precipitate enough immediately and a lot, then you risking losing of your whatever you pumping into the reservoir. So this is where it's critical to come with a significant mass of precipitate. This is what we designed. We form a lot of precipitate, and it acts as self-diverter. So it starts to block and the form, and this is how we basically achieve the efficiency. Yes, we precipitate a lot, and it helps in the pore space, obviously, to block and not to lose this into the. In terms of stages, the advantage is we can go because we're not relying on any other chemicals. So it's only basically two solutions, and if by the first application is not successful, you can chase with you can chase the second phase with the first one again, like a sandwich. Basically, you can repeat it without your previous stage. Basically, let's say if it carries some other chemical which reduce the efficiency, right? Okay. In our case, we can then just chase it, and the second application will build on the previous one.
Sure. We have a couple of questions here that I think in a sense are related. So the question here is, what about support or protection for the casing? So I think that's getting at the cement sheath is considered a permanent barrier, and it also makes casing a permanent barrier in a decommissioned well because it's preventing or protecting the casing from corrosion and maybe mechanical damage. So it says, if the idea is to plug the rock pores, does that mean there's no fluid column behind the casing? And so will there be protection? And maybe another related question about plugging of the well following your treatment, and maybe you can't answer this because it would depend on the jurisdiction and the requirements locally, but for the rest of the abandonment process, do you see any differences between using the Rockit product versus kind of traditional cement in the follow-up with what's required?
Oh, let me address it. Thank you. The first one. I think the first one, yes. If the way understood the question, if we can protect or seal the rock, basically, then there will be less contact of wellbore fluids with the casing, and long term we can provide the corrosion or protection. So let's say, for example, if there is a CO2 being injected in the reservoir, the CO2 eventually, if it's coming into the contact with some kind of legacy wells and there is a water available, so it will cause some corrosion of the your casing, even if this well specifically we're not injecting the CO2. So if we go and they protect those legacy wells and they form basically deep in the wellbore like a seal around the well, I believe that we can improve the corrosion resistance of the tubing and the casing for long term. This needs to be obviously tested, looked into. I like the approach and idea. Possibly at the moment, I think we need to focus on the field pilot and the most kind of simple application in this case, right? Now, speaking about the second one was to remind me about how if we can continue with the normal approach.
That's right.
Yeah, I think. Yeah, I think, and for again, depends on jurisdictions. I think that some still require having the cement plug installed. I'm not so again. So if your regulations still require for the cement plug to be set in the well, because we don't have any physical tool or anything sitting in the wellbore. Yeah, so we can continue with just this current procedures. In this case, you just don't have a flow from reservoir into your wellbore. So I believe that will even make your further procedure safer. So let's say you don't have gas bubbling through your cement.
Makes sense. Well, I think we've reached the end of the questions. So thanks, Oleg. Great presentation.
Thank you.
And if anything else comes up, as I said, we can return to any remaining questions at the end.
Thank you.
But great job. With that, turn it over to Lennox Leotaud with Well Armour. If you want to share your screen.
You guys able to see my screen?
Yep, and now it's in full screen presenter mode.
Okay. All right, so my name is Lennox Leotaud, and today I will be representing Well Armour Inc. I apologize for my voice. I'm dealing with somewhat of a cold today, but I should be able to get through the presentation, no problem. So I do want to start off by saying thanks to Innotech for giving us the opportunity to present our Well Armour product for this webinar. And in keeping with the time allotted for this session, what I will cover during this presentation is what the Well Armour is, what its characteristics or benefits are, and I'll touch on the applications it can be used in, and then share some performance results with you. The name of the company providing this technology is Well Armour Inc., and the product name is also Well Armour. It can either be Well Armour LT, MT, and HT, which I'll explain in more detail later. The Well Armour technology was introduced to the industry in 2017. And between 2018 and 2020, successful well abandonment jobs were completed, both in Canada, the US, and also internationally. After 2020, the inventor did not have the infrastructure to market the product properly, and the product became unavailable. At the end of last year, Well Armour Inc. Bought the licensing rights for this product, and they have the infrastructure to take this particular technology to the next level. So what is Well Armour? So Well Armour is currently a patented product in the US, Canada, and Europe, and it is comprised of non-toxic inorganic powders that, when mixed with water to form a slurry, it allows for a controlled set of the slurry, followed by immediate rapid compressor strength development. It is a thermosetting technology that can be used throughout the life cycle of a well. We use the term thermosetting because when the Well Armour sets, that transition from a liquid to a solid state is an exothermic reaction. And this heat generating thermosetting property allows for the use of Well Armour even in cold environments like Arctic or permafrost environments. The Well Armour slurry, depending on application temperature and set time needed, can, in a majority of cases, be a 2-component system or even a 3 or 4-component system of slurry. Shown here are all the basic components used to formulate a Well Armour slurry. All of the component materials are solid except for the Well Armour WT, which is a liquid. The makeup of a typical low temperature application Well Armour slurry is usually the Well Armour LT powder plus the Well Armour B added to water. LT stands for low temperature, and a typical low temperature slurry can be used from all the way up to 50 degrees C. Well Armour MT is the medium temperature component, and a typical slurry for a mid-temperature application is Well Armour MT plus the Well Armour B component. And the Well Armour MT can be used from 40 C to 70 C. The Well Armour HT slurry can be used from 70 C to 140 C. And this is just provided here as a guideline. In some cases, to achieve the set time targets, you can combine the LT with the MT and the B to achieve a particular set time. You can also combine a MT with a HT component to achieve a particular set time as well. The IT stands for inhibitor, and it's the component that's used to lengthen or adjust the set time of the Well Armour slurry. Well Armour WT is the component added to a Well Armour slurry when performing a water shutoff application. The WT gives the Well Armour slurry better resistance to water intrusion. To touch on some of the physical properties, one set, the Well Armour is an excellent insulator. It's also 100% acid soluble with 15% HCl, which is a important attribute or property. Let's just say you want to use the Well Armour as a temporary abandonment plug across a producing zone, for example. It does provide excellent bond both to steel and salt formations and in general any formation. It does not shrink, and in fact it slightly expands at the set point. The set material is thermally stable up to 900 degrees C, and the neat slurry density is 13.5 pounds per gallon. But that density can be adjusted if required or necessary for a particular job. We can lower that density or increase that density by the addition of other components to the blend. It is also impermeable when set. It has set permeability of 0.12 millidarcy, and that's gas permeability. The Well Armour MT, HT, and LT components are all of a medium particle size of 7 microns. So the Well Armour slurry does have a particulate fraction to it. That being said, unlike, say, a cement slurry, if you were to use the Well Armour slurry in a tight formation, or you're looking to squeeze it into a very, very narrow channel, even if you were to screen out the particulate fraction of the Well Armour slurry, the filtrate will still set. So that's a big difference, or a big performance property of the Well Armour as compared to, say, a cement slurry. Listed on this slide are the key performance characteristics of the Well Armour system. And the primary characteristic of the Well Armour is that it has zero gel strength generation. And that is when it transitions from a liquid to a solid state. That transition, which we call a right angle set, always occurs within 120 seconds. By contrast, a cement system goes through a gel strength development phase when it transitions from a liquid to a solid material. And without having to provide too much detail, it is this static gel strength development property of cement that contributes to its inability at times to shut off gas or other types of flow in a wellbore. Well Armour has no gel strength development, and its transition time always is within 120 seconds. Well Armour system can withstand contamination up to 30%, whether that's organic or inorganic contamination, and it's not going to affect, say, the ultimate compressor strength development of that Well Armour slurry. Let's just say your design compressor strength was 3,000 psi. With as much as 30% contamination, you're still going to achieve fairly close to that design compressor strength. Once the set is attained, the Well Armour slurry builds compressor strength rapidly. Typical compressor strength is between 2,500 to 4,000 psi. But per slurry design, you can achieve higher values than that. The Well Armour slurry, it's only temperature affects it. It is not affected by hydrostatic pressure or bottom hole pressure. Because of this, the temperature at the set point of the application, or the maximum temperature that the slurry will encounter during placement, is an important parameter. I would say both during job planning and design and during job execution, it's important to be aware of the temperature for that particular application. It is one set. If you have it in the wellbore and you need to drill it out, it is easy to drill with no cuttings. Average ROP when drilling it out is about 32 feet per hour, but from field observations, we've seen upwards of 40-45 feet per hour ROP when drilling out the Well Armour in the wellbore. It is also easy to clean up and so on from equipment after use. It is environmentally friendly, and it is immiscible in oil because it has a high affinity for itself. So it's not going to want to mix in non-aqueous type fluids. So the Well Armour technology does what cement and other fluids kind of do. This table compares the properties of Well Armour with cement and other commonly used systems. Of note, properties like the rapid compressor strength development, the fast transition, the tin fluid, allowing you to use it, pumping it through coil tubing or through a bit, are all very important or properties that differentiate it in a lot of cases with other fluids that are out there for use. Well armor can be used in various applications throughout the life cycle of a well. For example, during the well construction, the drilling phase of a well, you can use well armor for casing shoe squeezers, for stabilization of unconsolidated sand or shales, for moderate to total loss circulation. You can also use it as an alternate lead or tail slurry. It can be used on producing wells also to deal or address sustained casing pressure issues, water influx issues. It can be used as a temporary plug, as mentioned earlier, and it can be used to repair casing leaks. For well abandonment, you can use it again for sustained casing pressure, or surface casing vent flow, gas shutoff, and for general abandonment plugs as well. I wanted to give further emphasis on sustained casing pressure and surface casing vent flow, because it continues, as mentioned earlier in this webinar, to be a huge challenge in almost every oil and gas field. And well armor can be an ideal solution to address this issue owing to the benefits that it provides. So sustained casing pressure can present itself in a couple of ways, but for the case where the production casing annulus is not cemented all the way to surface, which is the case for most shale play development wells here in the US, what some operators are doing is they are running a flexible hose. It could be a 1/2 inch or a 3/4 inch hose through the wellhead valve, and they will run it to as deep as they can get it, and they pump a weighted brine. It could be a 10 pound per gallon brine, a 10.5, 11 pump per gallon brine or higher, and they do that to try and add some additional hydrostatic pressure to lower that sustained casing pressure. Well armor can be an alternate solution here if allowed, both by the operator and by the regulatory body, because you can also pump it through those small ID flexible conduits or holes, and instead of it being a brine, you'd have a system that can set in the annulus and give you a better isolation. And the properties of it will enable you to also do it in a rigorous capacity. It's environmentally friendly. The right angle set nature will be able to stop gas, and it's not going to dehydrate pumping through very narrow annuli or ID like cement would, for example. If addressing sustained casing pressure in that way is not an option, and for example, for well abandonment type scenarios, a more direct approach would be to squeeze well armor using through a retainer or through a packer into where the particular channel or gas flow may be originating, and you can isolate or shut off the gas in that way. Now, using a retainer or packer is at times or can be a preferred method to utilize the well armor slurry, because in this way you're able to trap pressure below the retainer or packer, allowing you to leave pressure on the system, whilst the well armor is able to transition from a liquid to a solid state. And again, the benefits here, as mentioned earlier, also applies. So lab testing in most cases is always done on the well armor slurry prior to a job. The test primarily done is a set time test, also known as a a thickening time test when done for a cement slurry, because the equipment used to perform the set time testing is a standard consistometer that's typically used to perform thickening time testing for a cement slurry. This chart here is an example set time test done on a Well Armour slurry, in which the temperature was ramped from room temperature to 72 degrees C, simulating pumping the Well Armour from surface to the reservoir zone. And once the slurry gets to the reservoir zone, there's a dwell time where the temperature remains the same. And in this particular test, and as you can see here, after about 57 minutes, the set point is reached, and you see the classic right angle set of the Well Armour slurry. And the set time for Well Armour is pretty predictable. In this example here, this is a Well Armour HT slurry without inhibitor added, and the red line is a Well Armour slurry with 1% inhibitor added. You can see that as the temperature increases for both lines of both slurries, the set time reduces, and for zooming in here at the 85-degree temperature, you can see the slurry that doesn't contain inhibitor gives you a 20-minute set time, and at the same temperature, the slurry with 1% inhibitor gives you a 67-minute set time. So the Well Armour slurry and the set times, or with the addition of inhibitor, it's pretty predictable and also repeatable. And the set time test that's performed in the lab is also pretty transferable to what you would see in the field when you use the system. So if you do a test and you get, say, 90 minutes in the lab for your set time test, under the same conditions in the field, that's what you're gonna have to work with, or that's what you're gonna achieve in terms of a set time with the Well Armour system. Here's another example of a set time test that was done at up to 160 degrees. The ramp time was 60 minutes, and you can see the set point here occur right at the 43-minute mark. And also provided here some compressor strength development, cross compressor strength results. You can see that 8-hour compressor strength values are around 48, 4900, and 24-hour compressor strength values are around 56 to 6000 psi. So that gives you an example of the compressor strength build of the Well Armour product or system. So shown here is a video. In this video is an example of the Well Armour slurry being mixed, and you'll see how it looks in the slurry form. Here's a picture, of some molds that were done after the Well Armour slurry was mixed. We poured it into some molds, and you can this just provided here as an example of how the product looks when it's set. And this video is a crude example because the Well Armour components do not require high shear energy for proper mixing. The Well Armour slurry can be mixed in any standard oil well cement mixing equipment. The Well Armour material, when sent to a well site, will generally be provided in 50-pound bags on a pallet. And so to avoid having to lift the 50-pound bags or use a forklift to lift the pallet up, say, to the mixing platform of a cement unit, if a jet mixer is available, it can be used to add the sack material to the jet mixer at the ground level. So for large volume jobs, the preference is to mix the Well Armour slurry on the fly. So you can add, for example, the Well Armour LT or MT or HT component or inhibitor as well into a ball truck, for example, and send that bulk truck to the well site location to mix the well armor on the fly. This is an example of the acid solubility of the well armor system. A test was done, this is the well armor cube that was used for the test, and a hot plate and a magnetic stir rod was used to stir the acid for the duration of the test. And this is 15% HCl. And you can see that after 120 minutes, almost 98% of the well armor was completely dissolved. And these pictures show at the particular timestamps, the amount of well armor that was dissolved. Return permeability testing has also been done on Berea sand cores to show the ability to remove well armor from a formation using acid if necessary. Some drillability testing, and this is just provided here as an example. We've already done jobs and have been able to drill out well armor successfully without any issues. But initially a small scale test was done where well armor was placed in 7-inch casing and a Baker underreamer assembly was used to drill it out. And for that test, an ROP of 25 to 30 feet per hour was achieved, and just using water circulated at 1.6 barrels per minute, we were able to transport the cuttings and get it out of the particular test setup. When using the well armor technology, there are some do's and don'ts that we always want to highlight or mention, because well armor is totally temperature and time dependent. We'll need an accurate estimation of the maximum temperature to be encountered during slurry placement. That's plus or minus 4 degrees C or plus or minus 10 degrees C. You do not want to mix the well armor slurry until you're ready to use it. You must mix the well armor components in the right order, and we in most cases would recommend the use of viscosity fluids. Small volumes of it, as little as 1 to 2 barrels, can be pumped both ahead and behind the well armor slurry to separate it, to limit any intermixing with the wellbore fluids in the well. Here's a case history example for which well armor was used in the DJ Basin, Colorado, during a plug and abandonment operation. So the well operator was experiencing 66 psi of Braden head gas pressure through the 9.5-inch casing. After pumping 4 conventional cement plugs unsuccessfully, the well operator decided to use well armor. Squeezing through a packer at 0.5 barrels per minute, 12 barrels of well armor slurry was pumped, of which 2 barrels was squeezed into the formation, and 10 barrels of the well armor slurry was left in the 9.5-inch casing. A squeeze pressure of 8,000 psi was left on the well armor slurry overnight, and when the well was opened up the following morning, the Braden head pressure was 0 psi. Here's a second case history in which well armor was used to shut off annular gas on a CNRL well in Calgary. During well abandonment, the operator needed to shut off annular gas behind the 4.5-inch casing. For this case, squeezing through a retainer, a total of 6.5 barrels of well armor LT was pumped, of which 6 barrels was squeezed through perforations at 25-45 feet, and 0.5 barrels of well armor was left in the 4.5-inch casing. The application of well armor was able to completely shut off the annular gas, allowing for the well abandonment operation to continue. So the in summary, the Well Armour is designed to do what Portland cements and resins, for example, cannot do. The Well Armour system always sets under 120 seconds with zero gel strength generation. And the set point is pretty linear, as discussed or shown earlier, and that lab testing and the set point that's attained in the lab is pretty transferable to the field. And we can achieve very low set time targets. We can also achieve very long set time targets if necessary for, say, we need to do a lubricate and bleed type operation or application, for example. The Well Armour, it expands at the set point and it builds compressor strength rapidly after setting. It is totally temperature and time dependent. It is unaffected by bottom hole pressure. Due to the low or the micron size particulate nature of the slurry, you are able to pump it through a bit. You are able to pump it through narrow IDs. As mentioned or shown earlier, it is acid soluble with 15% HCl. It can withstand contamination up to 30% and still achieve close to the design set time characteristics. And no special equipment is needed or required to mix and pump Well Armour. I do want to state that Well Armour Inc. currently only provides the Well Armour material. So for jobs, the well operator will be responsible for providing the pumping service company to mix and pump the Well Armour slurry. Open for any questions now.
Excellent, Lennox. We do have time for a couple questions here. So we have a question from Ken. How low is the temperature limit for the LT? Says, for example, 8 degrees C. We have some shallow and cold wells here in Canada.
So as shown earlier, it can be used at those cold temperatures. I would say that it's not shown here, but if needed, we can further accelerate the set of the Well Armour slurry if needed for very, very cold temperatures. But as I mentioned earlier, due to the fact that the set of the Well Armour slurry is an exothermic type reaction, that enables you to utilize it at very low temperatures as well. But if necessary, if it's very, very cold, say 15 or 20 degrees Fahrenheit, for example, we can further accelerate the set of Well Armour for those very cold environments.
One here from Max Olson. Understanding there might be some confidential information you can't share, but can you provide more information on the product's chemistry?
That is right. There isn't, I mean, for questions like that, we would prefer that, people reach out to us directly and we can share more direct, detailed information under or via an NDA. But in general, what I would say is that what we are working with is a magnesium oxysulfate type slurry.
Yeah, that's helpful. Thanks. There's two questions here that I might kind of lump together. They're both related to the long-term, I think, kind of durability of the product. So one, have you done any long-term testing to look at how the set material behaves under different wellbore temperatures and pressures? But also, Colin Witt has mentioned for the acid testing, have you tested the solubility with carbonic acid. So, or I think it's looking at acid solubility in use and the durability of the product rather than cleaning up with hydrochloric.
I would say in general, long-term integrity of the set Well Armour slurry, once it's not affected by, say, low pH fluids that are able to flow past it or affect it, it should be able to, last for forever. So the inventor, we'll have to get back to you guys, or if we can get the contact person who asked that question, we can get back to him to provide information on if it's been tested with, say, carbonic type fluids. But I would say in general that low pH fluids would be a concern for long-term integrity.
Makes sense. So there is just a comment here about getting your contact information. We will make that available, and at the end of the presentation here, I'll have a slide with all of the presenters' info. So in the interest of time, I think we're going to move on, and we'll come back to any other questions at the end if there is a chance. Again, thanks, Lennox. Great presentation. So our final speaker today is Craig Brown from UVT Solutions. If you want to share your screen, Craig, and take it away.
Share.
Let's start talking.
Are we on now?
Yep, I can
hear
hear you. Can't see any slides yet.
I don't.
Oh, we don't have
We
slides.
don't have slides.
Okay, no worries. Go ahead.
All right. UVT is a company that we are based out of northeastern Oklahoma. We were, I've always been in the drilling business before. Owned drilling rigs. My grandparents have owned drilling rigs. We've always been on the drilling rig side and never on the production side. I think that's one reason why what we've come up with, we were out of the box on the other side, because never dealt in production, just drilled wells and moved on. We found out through different things that we had a huge problem here in northeastern Oklahoma and across the whole state, where people were setting in bridge plugs and cement, and they were leaking. And so I'd owned a test facility in my life. So my wife and I have become really good friends with the University of Tulsa, who has quite a petroleum engineering department, and went over and talked to them and said, what is the issue? And they basically told us, they said, well, bridge plugs are not designed to eliminate methane gas from escaping. They're designed to hold weight. And so, and they're putting cement on top of a bridge plug, and the bridge plug, the cement cracks. So basically, we're putting two products in a well, calling it plugged here in Oklahoma, and neither product worked. And so I said, well, being that we were in the drilling business, I was well aware of a lot of the machine shops around here over the years. And I said, well, what if we built something that would? And they basically told us they didn't think you could do it. So we got with some machinists that we knew, and we built some seals and many failures. And we were trying to take the place of a bridge plug, because we knew through TU that they didn't believe it. Didn't matter what we did, cement was not going to work. It was going to crack and allow the methane to escape. So by building this seal, we went in the machine shop and built our own air chambers and everything. And we went to TU. We put two seals actually in a casing, and we set a bridge plug in casing as well. So we took them to TU and put them under test. Under 200 pounds of pressure is as high pressure as they could go at TU, being that they were in the city limits of Tulsa. And so our seals did not leak a nano bubble in 2.5 years. They finally told us to take them home. They weren't going to leak. And the bridge plug held less than 48 hours. It was at 0. So we knew we had something then, and then we had to go figure out how to make it feasible for the oil field people to use. So we got with Aberdeen Dynamics, which is one of the biggest hydraulic companies in Oklahoma. We built a hydraulic system of our own where we could set these hydraulically. Well, then, as it developed, it's been a 4-year process to get here. As we kept developing this, we found out the only way to get it into the oil fields were to be able to make it available to service companies, wireline companies, to be able to do this, because it was going to cost way too much money for us to equip all these hydraulic trucks to set them. So we got with a couple of wireline companies. Ranger Energy Services out of Houston had been following our technology on. We'd been on a couple of podcasts with different items that we built. And so they came up and they wanted to run some tests. We ran multiple tests. We set a seal. We took it to 10,000 pounds of bottom hole pressure. It didn't leak. And they wanted to see what the push out pressure was. And we were pushing out the bridge plugs at about 8,000 pounds. We took ours, pressed it out. We went to 50 ton. We were able to break it loose. Because when ours is set, it's set with what's called cold welding. When you pull the wedge up into the sleeve, it will compress to the wall, and it's done at a slow enough speed. It only takes us, well, I'm not going to say, but the cold weld pressure is less than 400 pounds to get your cold weld when you pull it. And so if your casing's got bad old casing, you can still set these seals in it. And then we got into a deal where some of these casings were eating up really bad. And so we built a 20-foot liner that we could go in and run a liner in there that's made of marine aluminum as well. And we can actually set a seal inside of the liner. One of the unique things about our system is all we need to do is know the ID of your pipe. And we have the numbers here where we can build the seal that will do it. We'll fit it. We can't go below 4-inch, and we can go to any size big that you need to go. We have capabilities of building up 3,000 seals a day, so going to scale is not a problem. We have availability of the pipe, the marine aluminum, to build the seals out of. And we can also build one out of Teflon. The Teflon seal was designed to have absolutely no problems with the Teflon. It just won't hold as much weight. It will compress into the well instead of break loose. We really don't know how much weight it would take. We took 20 ton, and we quit, or we were afraid we were going to push through it. But it's a neat system that can be used, and we retrofit off of. We were able to set it off of a Baker 10 setting tool, which made it available to every wireline company in country and Canada and anywhere else, because everybody's carrying a Baker 10 setting tool or a Baker 20 setting tool. And we've got 2 different companies here. We've got it under test in Houston right now. They're testing the H2S test, and it's being tested at 30,000 parts per million of H2S. And of course, we're pretty sure it's going to pass, but we'll find out. We were hoping we would be through before this. Sorry about that. We were hoping we would be through before this meeting, but we won't have results until Thursday, and we'll make those public when we get them. We're approved in New Mexico, Texas, Colorado, Wyoming, and we're about to be, we're close to that. What we do is let customers drive where we get approved. when a wireline company contacts us and wants to be able to set the seals, then we come back and then we go to the state, get approval. We've not been turned down by anybody yet. We have the University of Tulsa has been doing all the testing for us. So we have third-party testing. We have white papers on both of our products. Our company feels like the hardest thing to do is put a standard bridge plug down and put cement on top of it and expect it to hold. We don't feel like that works. I've learned about products here today that would be great to sit on top of our seals. But, all of our states around here require 2 barriers. And I don't know what the regulations are in Canada, but here it's 2 barriers. And, for our company, we feel like they're putting 2 barriers in there and neither one of them work. We don't feel like bridge plug works. We don't feel like cement works. So basically, we feel like we're plugging here in the United States. We're not really plugging them well. So that's really pretty much it. I've got a guy here. There's a company here with us. It's that process of switching over from a standard bridge plug to UVT seal. His own wireline company. If anybody has wireline questions, he's here with us. Availability of those things within a week, we can have them shipped out. We're set up with a large manufacturing company here. As far as testing, we've done all the testing. We've set them. We've got them going in on federal land within the next 2 weeks up in the Osage Reservation. So we'll be able to be approved on any federal land. I mean, we are trying to take the place of a bridge plug in the U.S. and I feel like we're headed there. So we're open to any question you guys have.
Great, thanks, Greg. I have a question. So I think as you mentioned, a bridge plug isn't considered a permanent barrier. I think largely to the elastomeric sealant components, they're just not going to last forever. But at the same time, when you do place cement on top, it's hard to pressure test that cement barrier with the bridge plug underneath. So a plug, a mechanical plug in the casing that is considered permanent could be a big benefit. You've done some corrosion testing, and it sounds like you're doing some H2S testing now.
Yes, sir.
What is involved in Oklahoma or in the other states you're dealing with approving the plug as a permanent barrier? Oh, you're muted. I think maybe somebody muted you because of the feedback.
Am I back? Can
Yep,
you hear me now?
all good.
Okay. Our biggest deal was to get it approved as a bridge plug, to get it out there and to prove what it would do. Because, it's my wife and I, and we're not a big company. We're the 2 of us. We funded this deal ourselves. And so we were more interested in getting the bridge plug removed than I am what they put on top of it, because I know our seal will hold. And so I've got 16 grandkids between us. And to be honest with you, my grandparents, my father, all of us have been in the oil field forever. And I don't like leaving behind for my grandkids to clean up the mess that we've created. And it's not done I'm not saying this has been done on purpose. We thought we were doing them right the way we were plugging. But with the new technology and what we've learned, we're not. And it's kind of a deal where, okay, let's figure out some way to stop it. And I'm not saying 10 years from now there isn't going to be better technology. I hope there is. But in order to get people to take the steps to get to where we can start, the first thing we got to do is stop coming up the pipe. I mean, outside of the pipe, okay, then we can squeeze, we can do whatever we want to do. But till we get it stopped from coming up the pipe, it doesn't matter what we put down there. It's going to come see us. And here, they go down and cut pipe off 1,000 foot below ground level or further. Well, and they're covering it with a bridge plug and cement. When it starts leaking, we've got no way to get back in there and fix it. I mean, the problem, now we got a bigger problem. If we can at least get them to put our seals on bottom, and we've had many meetings with the Corporation Commission in Oklahoma and in Texas, that, you know, we got to start somewhere. And to me, the bridge plug is the first place to start. It's not designed to hold pressure. It's designed to hold weight. And I would like for Jody to talk to you guys about the problem with the bridge plug. A lot of these wells around here are so old that when we're setting a bridge plug, the dynamics of setting a bridge plug, they're knocking holes in the pipe, and they're doing more damage by setting a bridge plug than they would if they leaked wet screwed in the pipe and drive away. Because we have no way of fighting it. Jody, if it's all right, I'll let Jody explain to you why they switched over the UVT seal.
Right. I've got 35 years in wireline, grew up, my dad done it, so this has pretty much been my life. And when I saw Craig and Ann's plug for the first time, the simplicity of it just blew me away. All the mechanical is gone, and any mechanical plug, any downhole system that we deploy in the oil field is driven by, you know, explosive over hydraulic. You create a reaction and you knock loose a set of slips, carbide, tungsten, or ceramic. Those slips actually bite into the inside of the casing as you try to compress the rubber element in the center of it in hopes that it seats against your casing, and then draw the bottom sets of slips up, get them to release that also bite into the casing. Well, if you're up here in pressure control, when we're trying well containment to withhold the pressure while we get our tools in the hole, we run 10K iron on top of it. If a cast iron bridge plug is accidentally set off or a tool malfunctions in the lubricator and that plug is set in my pressure control iron, it never sees the light of day again. But yet we'll put casing a third the thickness down hole and set these over and over and drill them out and set another one, and we pretend like we're doing the right thing. But you get into these casings that are 50, 60, 70 years old, and these CO2 floods and these H2S zones and all these other areas where your pipe is destroyed anyway, and then we set a bridge plug in them. For every leak you're trying to stop, you're creating at least two more. The simplicity of drawing the wedge into the sleeve system seats the entire way around the casing without any jarring or mechanical destruction to the inside of the pipe. And that's the simplicity behind this is what makes it just genius in its own. The other advantage is over a mechanical set plug, you're no longer worried about overbalance and underbalance or unseating a bridge plug because you don't have enough pressure above or below it. With the pressure coming from the bottom side, you continue to push into the wedge, which drives into the sleeve, and vice versa the other way. You're forcing the sleeve down onto the wedge. It compresses no matter where the pressure comes from, and all the instability we've always tried to outrun with bridge plugs by dumping sand and rocks and cement. We've removed that, but we're also eliminating further casing damage. And like Craig was saying, the real big benefit, especially here in the States, there are a lot of wells that were drilled during the wars. And during those times, there are a lot of oddball sized casings in the ground that they don't make plugs for. We can machine a wedge or a liner for any of these things and actually go back and remediate a lot of problems that no one's tried to fix.
Yeah, thanks, Jody. Good to hear your perspective for being out there and seeing work in the field. We do have a question here. You mentioned re-entering wells, so just a quick question: is the plug drillable?
Yes. Very drillable. Marine aluminum be much easier to drill out than a bridge plug.
We had a Teflon in a well about 2 months ago and drilled out. The company actually showed up with the wrong size tubing, so we had to wait on a reverse unit to reverse drill and circulate it out. And even at that speed, the Teflon drilled out in 7 minutes.
I don't see any other questions coming in, so thanks for your presentation. And
Okay.
maybe I'll just ask all the presenters to come back on. And as I said, we can open it up here for any final questions. I have one for you, Lennox. I didn't ask earlier in the interest of time, but since there's a couple minutes here, there are interest in these alternative barrier materials for thermal wells here in Canada. So these are steam-assisted gravity drainage or cyclic steam stimulation wells, where the steam injection temperatures could be, 250 even up to 300 degrees C. So one of your slides there had the Well Armour's thermal stability, I think up to 900 degrees Celsius. And I think there's quite a few different applications where these materials could be used in thermal wells, either where they're set at low temperatures and then need to withstand those steam injection temperatures, or maybe to repair a well that's going to be or has been in service and will be put back into either injection or production. So could be hot, could be cold. We'll see high temperatures at some point in its life, or has to meet the regulatory requirements for temperatures in that area. So with all that, I'm wondering what type of testing you've done to show the Well Armour's capabilities to withstand those high temperatures, maybe during setting, but also in service.
So we will be definitely interested in looking at those types of applications. And you're right, Well Armour slurry in its set state is thermally stable up to 900 degrees C. I don't know what or if any testing has been done to show the applicability of the system at such high temperatures, say upwards of 500 degrees C, for example. The inventor is on, he's one of the attendees listening to this presentation right now, but he's unable to speak. So I think that's a question that we'll have to get back to you with an answer on, Jonathan. But in general, that type of application is something that if the placement temperature is not too high, yes, the Well Armour slurry is applicable to be utilized in those steam, injection type wells.
Cool, appreciate it. I just wanted to ask that question while I had the chance here. So.
Jonathan, pardon my interruption. I can share Tim's microphone and camera, Tim, if you're okay with that to answer the question.
Oh, there he is. Says, yeah, Tim Sharp.
I got Brian on here right now. He's the inventor, so I'll let him answer that high temp question.
Yeah, technology is used in furnaces, the lime furnaces. So we know that the temperature stability or temperature breakdown is very high. It's certainly in excess of 800 degrees centigrade. And it's important to remember with these materials, it is an exothermic compound. So if you're using it at very low temperatures, it self-generates heat internally. So at the very low temperatures, it's going to simply take longer to get to that set point. And you would have to build that into any program that you were doing at a very low temperature. But it's going to set regardless of whatever the temperature might be. And once it reaches a certain internal temperature, then it triggers a set point. So you've got this flat viscosity profile up to the set point in all cases. with zero gel strength generation. So you're eliminating channeling or the possibility of channeling between the fluid and the set states. And the fact that it will bond into organic material as well as inorganic material, I think is very important, because a lot of formations such as shales, etc., have organics in them. They're not rock. So it will withstand this contamination with organic or inorganic contamination, and it will physically bond into the shale. So if you take material and mix it with shale or mix it with any of these other materials, in many cases it will simply make it stronger, simply increase the compressive without altering the set characteristics. And the linearity is critical because it has to be predictable. It is absolutely predictable as to the set point. It's accurate to within minutes.
Cool. Thanks for your response. I don't see any other questions coming in here, so I think we'll wrap up. We're mostly on time. I will just share my screen one more time here. Just like to say a few thank yous as we wrap up here. So of course, thanks to our speakers, great presentations. Always loved learning about new and novel ideas that are being developed. Also like to thank John Hagan with Innotech's, Alberta Innovates communications team. He did all the work behind the scenes to get this organized. My email address is there on the screen if you want to follow up for any reason, want some more information, or if you're a technology developer and are interested in participating in one of the future webinars, feel free to send me a message. So again, thank you for attending, and we'll see you next time.